So everything we've been learning about in this unit has come down to this. Intermolecular forces are incredibly important. In our planet, in our world, in our everyday life, they explain so many different properties of how matter behaves, and it explains so many natural phenomena on a day-to-day basis. I cannot underscore the importance of intermolecular forces enough. We're just going to basically scratch the surface of what some of these properties can be. I'm going to try and tell you as many of the different natural phenomena that are related to this as possible, but there are so many more. So let's just quickly review here. What different types of intermolecular forces are we talking about? Well, we have hydrogen bonding, which tends to be the strongest intermolecular force. Again, we're limiting our scope here only to covalently bonded materials. We are not looking at ionically bonded materials in this unit. Underneath that would be dipole-dipole. Those are the intermolecular forces felt by polar molecules. And then, of course, underneath that, the weakest of our lovely intermolecular forces would be London dispersion. Now, it is possible to compare two different molecules, two different nonpolar molecules that have only London dispersion forces. Remember that that's kind of like the jello jiggler of forces. When the electrons wobble back and forth inside of that molecule, it creates a temporary dipole. Therefore, the more electrons that a nonpolar molecule have, the more polarizable or the more jiggle that molecule will have, and thus may have stronger London dispersion forces. So if you're ever asked to compare two nonpolar molecules, the nonpolar molecule with more electrons will have a stronger intermolecular force than that has fewer electrons. So now off to our first force, melting point. Melting point is one of the easiest things that we can actually compare in chemistry because all we have to do is melt the substance and monitor the temperature. So melting point is the temperature at which a substance will melt. So again, just as far as we need to understand about melting point is that temperature at which a material is going to transition from being a solid into a liquid. And I want to take a microscopic look at what the inside of a crystal may actually look like, a solid crystal, that is. Here is a great example. This is just some high quality H2O. Couple things to notice here. Notice that the little red and the little yellow spheres are indicating the oxygen and the hydrogen on the inside of the molecule, and yet they're being connected by these little green sticks. Those little green sticks are indicating the intermolecular forces holding that crystal together. And before we completely leave this, I just want to show you a different view of what that crystal would look like. Notice anything geometric happening on the inside? Very regular, very ordered. I wonder if simply the intermolecular forces which create that solid create any other natural phenomenon. Maybe like the six-sided natural shape of every single snowflake known to man? Absolutely. Intermolecular forces can be used to explain this, but back to melting point. I have this cute little simulation here, and I will play this for you. I want you to notice first, before I play this, look at the inside of the cup. It is filled with ice right now. And do you notice that little hexagonal pattern on the inside? Again, the intermolecular forces are stable, they're regular, and they're holding that crystal in place. But now what we're going to do is to slowly increase the temperature. Notice those little molecules wiggling in place? And now as the crystal starts to melt, notice what has changed. The pattern has broken. The molecules are now moving freely across the entire glass. And those intermolecular forces are much, much weaker. So again, back to this ordered crystal. If we take a look at one H2O molecule, the little black sticks that are drawn in between the red and the blue spheres, those are covalent bonds. They stay put. They do not change during the melting process. But when we take a look at what's holding each water molecule to another water molecule in that ordered crystal solid, we notice that they are called intermolecular forces, in this case, hydrogen bonding, which is quite strong. And it's these intermolecular forces that need to break during the melting process. Therefore, the stronger the intermolecular force, which is what needs to break to get this stuff to melt, the more energy it's going to take to melt that substance. So in other words, the higher the intermolecular force you have, the higher your melting point. Let's take a look at another phenomenon. Boiling point. Very, very keenly aligned with what melting point is all about. Boiling point is the temperature at which it takes to boil a substance. We're going to be transitioning this time between liquid and gas. And it's important to note that even though there are less intermolecular attractions in the liquid state, there are still some. And what we need to do is to overcome those intermolecular attractions so that the little particles can leave the liquid, which is what you're seeing at the bottom, and go into the gas state, which is what you see at the top. In the gaseous state, I'm not going to tell you that there are no intermolecular forces, but there are so few because the molecules are simply spaced too far apart. In the liquid state, you're still going to have some, but way less than if you were an ordered solid. So, again, in order to become a gas, you're going to need to break intermolecular forces. Therefore, the stronger the force, the more energy you're going to need to boil that material. So the stronger the force, the higher the boiling point, the higher the temperature is going to be to take that material to boil. Let's take a look at yet another property, something called viscosity, which you may have seen before. This is what we would call the thickness of a solution. Take a look at the screen right now. You see being poured into the beaker two different materials that have two different viscosities. I would say that the material over to the left-hand side is less viscous, less thick, than the material to the right, which looks extremely thick. Here's just another visual example here of materials that may have low viscosity all the way up to high viscosity. The materials that have high viscosity tend to want to stick to itself. It gets all globby and gluey. Whereas if you have low viscosity, it's very easily poured from a container. It doesn't want to stick to itself. Speaking of that sticking to itself, here's a great picture to kind of explain what creates this thickness of a solution. It's important to remember that the particles on the inside of a liquid are attracted to each other by intermolecular forces. When these intermolecular forces are strong, the particles are going to be very attracted to each other. And if they're very attracted to each other, that's going to create a very viscous solution. So in this case, the stronger the intermolecular force, the thicker or more viscous the solution will be. One more property to talk about with intermolecular forces: surface tension. Surface tension is one of my favorite intermolecular forces because it's extremely visible. We're going to go back to this lovely same picture here. Remember that intermolecular forces are forces that are holding all of these liquid molecules together. But we're going to kind of narrow our scope here. Instead of looking at the entire liquid, we're only going to be looking at the molecules that separate the remainder of the liquid from the air that's surrounding it. Notice that each one of those molecules is attracted to each other, creating essentially a net at the top of the liquid. We call this net, or net-like force, surface tension. Now, importantly to remember again, the stronger the intermolecular forces, the more those molecules are going to be attracted to each other. And because these molecules are connected then at the surface like a net, it creates literally a surface that you can see, that you can actually touch and feel and play with. The stronger the intermolecular force, the stronger that surface tension is going to be. We can see this very notably when we're trying to drop a liquid onto anything or through the air. The stronger the surface tension, the more the liquid will be attracted to itself rather than, say, to a tabletop. So we'll actually see that liquid bead up off of that surface. This is the exact same reason why when it rains, a drop is the shape that it is. Water has hydrogen bonding. It's extremely attracted to itself, and its surface tension is so large that when you have some of it falling through the air, it creates as little surface area as it can and creates a drop-like structure. Even cooler than that, nature has also taken note of surface tension, and water with its hydrogen bonding has a very large amount of surface tension. The little insect that you see on the screen is called a water strider. It can actually spread out its body weight over the top of water's surface without actually breaking the surface. It can use it to walk on water. It's super cool. So again, taking a look at this, you can see that the little water molecules are so strongly attracted to each other that it creates a net on the top of that water. And the water strider simply uses it to its advantage, spreading out its all body weight over top of the surface of that water without actually breaking that surface tension. One more property. I know there are a lot, and there's even more than what I've been mentioning in this little video. You should probably look some more of these things up. Capillary action. Capillary action is super cool. Here is a little GIF to try and show you what capillary action is. You can see that there's a tiny tube. Nobody is putting any type of pressure on the outside of this tube. It's simply being lowered into the liquid, and the liquid is climbing by itself into this tube. So what's happening here? Simply, you lower this tube into the water, and the water climbs up into this tube. Water, again, with hydrogen bonding, a very strong intermolecular force, means that the water molecules are not only attracted to themselves, but they're also attracted to other polar items, which glass is. So if we lower a small tube into water, you'll actually notice that the water molecules become attracted to the glass and are able to climb up the sides of that glass. And we call this phenomenon capillary action. So the stronger the intermolecular force is going to be, the more this liquid can actually climb up on the inside of a straw. Now, what's really interesting is that nature actually does use this phenomenon. We'll actually see capillary action and water's ability to climb up these small tubes on the inside of trees. This is how trees are actually able to passively soak water up from the ground and up into their crown. Yet one more intermolecular force to consider is vapor pressure. Now, this is the pressure created by a gas. And to create pressure, you need to have a particle crash into the wall of a container. So here are 3 containers. We can see that in the blue container, there are very few gas particles, and in the red container, there are quite a few gas particles. Now, why might this be? Well, in the blue container, we actually have strong intermolecular forces. What this means is that the molecules are highly attracted to each other. So they want to actually stay in the liquid state. But over at the other side of the spectrum here, we have a chemical that has low intermolecular forces. That means that the particles themselves are not very attracted to each other. Those intermolecular forces can easily be overcome, and the particles easily slip into the gaseous phase. Therefore, the blue container, we would say, has low vapor pressure. There are very few gas particles on the inside of that container to bump into the container, creating low pressure. And at the other side of the extreme here, in the red container, there's a large number of gas particles in that vapor state. Many particles that can crash into the container and create pressure. So again, the stronger the intermolecular force, the higher the vapor pressure. The lower the intermolecular force, the lower the vapor pressure.